Hello, bachcho. How are you? Fine. Good. Today our topic of discussion is Wheatstone Bridge. Okay, it is from the current electricity chapter, and from which after Wheatstone Bridge now we'll be going for that meter bridge. Okay, so because that meter bridge also based on the principle of Wheatstone Bridge only, na? So that's why we have to understand this part very clearly. Okay, this is from the chapter number 3 of class 12. Topic is Wheatstone Bridge. Okay, so what is the Wheatstone Bridge? Let me see. Wheatstone Bridge. Wheatstone Bridge. Okay, it is very simple, guys. It is simply quadrilateral network of 4 resistors. Bus enough. 1 resistance, 2 resistance, 3 resistance, and 4th resistance. Okay, P, Q, R, S. Okay, it is a quadrilateral network of 4 resistors in which one diagonal is connected through a galvanometer. Okay, one diagonal is connected through a galvanometer, and the other diagonal is connected through a battery, a cell. So I can draw this other diagonal here. I can draw the other diagonal here. Okay, same thing I can put here also, but this will be overlapped. It looks very odd. Okay, that's why I am drawing here. This is a cell. So it is simply a quadrilateral network of 4 resistors P, Q, R, S, in which one diagonal is connected by a galvanometer, another diagonal is connected by a cell. It is simply a Wheatstone bridge. Even you can put this galvanometer not in diagonal here also, and the cell in this diagonal also. You can interchange also, no problem. Okay, you please write down definition. It is a quadrilateral network of 4 resistors in which one diagonal is connected through a galvanometer and the other diagonal is connected through a battery or cell. But it is very important that at the very outset we should know the definition. So it is the basic definition of a Wheatstone bridge. And why this is to be studied, okay, and what's the use of it? The basic use of the Wheatstone bridge is to know the value of unknown resistance. For example, P, Q, R, S. Out of these 4, say you don't know the value of Q. Knowing the value of P, R, and S, we can easily calculate the value of Q. How we'll be discussing. Okay, but the basic use of a Wheatstone bridge is to know the value of unknown resistance. Okay, write down please. It is used to measure the value of an unknown resistance. Okay, great, you are doing well. Now we will be discussing a special kind of Wheatstone bridge which is called balanced Wheatstone bridge. Okay, I am going to rub it. If you are late in copying, no problem, put a pause on the video and just copy. What I am going to discuss now, balanced Wheatstone bridge. Okay, you can also write down please, balanced. It's a network of resistors or nothing else. Okay, Wheatstone bridge. A Wheatstone bridge is said to be balanced if it satisfies the condition. Which condition? Ratio of resistance of P to resistance of Q equal resistance of R to S. This is called balance condition of Wheatstone bridge. Very important. Very important. Okay. You see, I am taking this is P, this is Q. Na? This resistance divided by this resistance must be equal to this by this. Huh? You see, it is not in cyclic. Huh? You may get confused. This is P, Q, R, S. It is not like that. Huh? P, Q, R, S. Okay. Normally it is written like that only. Okay. If you put R1, R2, R3, R4, then what will happen? R1 by R2 equal to R3 by R4. If you put R1, R2, R3, R4, then what will happen? For the balance condition, R1 by R2 equal to R4 by R3. Okay. Left divided by right equal to left divided by right. You can do the reverse also. Right divided by left is equal right divided by left. Okay. That is not an issue. Good. But why it is called a balanced Wheatstone bridge? Okay. To understand this fact, we have to take one example. Okay. See, say I have a resistor of 2 ohm and another resistor 4 ohm connected in series with a battery of 12 volt. Okay, just an example to explain all these things, nothing else. Now you see, what is the ratio of resistance? 1:2. Yes, 2:4 means 1:2. It means the applied voltage 12 volt will be divided in the ratio of 1:2 along the resistance. So what will be the voltage drop here? What is the voltage drop here? Total voltage divided by 3 part into 1 part, because voltage drops according to the resistance only. Na? More resistance, more voltage will be dropped, more energy will be liberated. We have already understand. Na? Voltage is nothing but energy per coulomb. If it is 12 volt, it means 1 coulomb will carry 12 joule. So this energy, out of that energy, some energy will be dropped here, some energy will be dropped here. Obviously, this is more resistance, more energy will be dropped. Resistance means opposition, na? Disturbance. Okay. So here voltage drop is 4 volt. Now voltage drop at 4 ohm, what will be? Total voltage 12. We have to make 3 parts into 2. Okay. It will be 8 volt. And here I see the voltage drop is 4 volt. Here I see 8 volt. Total 12 volt. Okay. That Kirchhoff's second law also valid now. Na? Total voltage supplied and voltage drop both must be same. Good. Take another example. Say it is not connected here. It is connected to another set of resistance. Okay. Say this is 4 ohm, this is 8 ohm. Okay. Now let me see what is the voltage drop here and what is the voltage drop here. Okay. See, Now what is the ratio? 4:8. It means again 1:2. So what will be the drop here? The drop will be out of 12 we have to make 3 parts because ratio is 1:2. Out of that 12 by 3 we have to take 1 part, one part. So I get same 4 volt. For the 8 ohm also 12 divided by 3 into 2 parts. Again I get 8 volt. It means in this condition also I get 4 volt is dropped here and 8 volt is dropped here. Remember it was same here also. It was 4 volt, it was 8 volt. Okay, it was 4 ohm. Now you see, if both the set of resistors are applied together, now what will happen? It's a very important issue. Remember, you have to draw the figure 3 times. First with that 2 ohm 4 ohm, second with that 4 ohm 8 ohm, and third as like that I have combined it. Okay, now you see, now what will happen? As it is 12 volts, so the potential difference between these 2 points will be 12 volt, these 2 points also will be 12 volt, and these 2 points also will be 12 volt. Means this set of resistance also getting 12 volt and this set of resistance also getting 12 volt. And here I see 4 volt will be dropped and here also I see 4 volt will be dropped. Now you see, think of the current going this way. It is taking 12 joule per coulomb, out of which 4 joule will be dropped. So 12 minus 4, what will left? 8. To 8 joule will be there. But at this point you can say that 1 coulomb charge will have 8 joule. You can say that the point of this potential is 8 volt. Exactly same way, think about this current. The current is going this way, okay, and it is bringing 12 joule per coulomb. Out of this 12 joule, 4 joule will be dropped here. Okay, 12 minus 4, what will be left? 8. 8 joule energy will be left per coulomb here. You can see the point potential of this point also 8 volt. Are you getting my point? Now you see, this point and this point will be at the same potential. If you join this 2 point by a resistor also, then also no current will be flowing. If you join these 2 points through a galvanometer also, then also you are not going to get that deflection because this divided by this equal to this divided by this. Okay, now you see, this figure and this figure both are same. Are you getting? For P I was taking 4 ohm, for Q I was taking 8 ohm, for R I was taking 2 ohm, and for S I was taking 4 ohm. Are you getting my point? Do you understand? Able to correlate both the figures? Okay, great. That is why this condition, ratio same, this condition is called balance condition. It means this point and this point will be at the same potential, no current will be flowing through the galvanometer. Okay guys, I am going to rub it. As you know, you can just copy it properly, giving a pause to the video button. You see, at the balance condition, at the balanced condition, no current flows through the galvanometer. Why no current flows? Because the potential of both the ends of galvanometer remain same. Okay, so this point and this point will be at the same potential. It means this point and this point will be at the same potential if it satisfies the condition P upon Q equals R upon S. Okay beta, now we are going to derive mathematically this expression. Okay, derivation of the balance condition. So you just copy it. I'm going to rub all these things, guys. Derivation of balance condition. But you have to draw the figure, this figure once more. Okay. Derivation of balance condition. Derivation of balance condition in Wheatstone bridge. But I am putting WB, but I think you are not lazy enough. You will be putting Wheatstone bridge. Okay, good. You see, let us assume that some current is flowing in this branch, and out of which I1 flows this way. Okay, I2 flows this way. It means I1 plus I2 emerging from the cell. You can see out of I1, Ig flows through the galvanometer, and rest I1 minus Ig will be flowing through Q. Okay, I am distributing currents in the branch using Kirchhoff's first law. Okay, at any junction point, sum of all the currents should be zero. So as I1 is entering to the point, Ig is outgoing. The rest outgoing amount must be I1 minus Ig. Okay, good. Now you see I2 is coming this way and Ig is coming this way. They are meeting at this point. So what is the current outgoing? It should be I2 plus Ig. I2 plus Ig must be going, na? Ig coming this way, I2 coming this way, both are meeting at this point, so the outgoing current must be I2 plus Ig. Now again you see at this point, I2 plus Ig going this way, I1 minus Ig coming this way, and if you add it, you will get again I1 plus I2. It means from the battery, I1 plus I2 coming out, and in the battery, that I1 minus I1 plus I2 again entering it. Okay, it means Kirchhoff's law again valid. Okay, using first law, we have distributed current everywhere. You can add it, I1 minus Ig and I2 plus Ig. You are going to get I1 plus I2 only. Now you see in the loop, name the loop, give the name to the corners. Okay, I1, I2, sorry, A, B, C, like that. Say this is A. Say this is A, B, C, D. Okay, in the loop A, B, D, A. In the loop, you see properly, A, B, D, A. Which loop I am talking about? This loop. Okay, in the loop, as you go from A, you will see voltage drop here. What is the voltage drop? I1P, current into resistance. But why it is minus? Because as you go, you will see less potential later. Okay, final is less, initial is high, so change will be final minus initial. Change is always final minus initial. Change is always final minus initial. Difference is always bigger minus smaller. Okay, so as we are counting change, potential change, so final is low. Why it is low? Because current is going this way, and I know that current always flows from high potential to low potential in a resistor. Okay, okay, you are going from point A to B. You have reached P. Then you have the up till now no potential difference. Here you are going to see the potential difference, high, low, minus Ig into capital G. What is capital G? It is the resistance of the galvanometer coil. You have reached this point, then you come this way. and this will be high, this will be low. Current is going this way and you are coming this way, so that's why it will be positive. I to R must be equal to 0. Okay. Now if the galvanometer shows no deflection, if Iz equal to 0, this equation will be in the shape of minus I1P plus I2R equal to 0. I1P equal to I2R, it means I1 by I2 equal to I1P, I2R, I1 divided by I2 equal to R upon P. Okay, this is equation number 1. I am putting this equation here because I need some space so that I can rub this part. Okay, beta. Fast, copy it fast. Give a pause and copy. I am going to rub it. Then in the loop, you see I have gone through this loop only, this loop. Now I will be going through this loop because I need 2 loops for 2 equations so that I can compare it. Good. Now you can do one thing. You just see once more. Try to understand all these things how I have done. Okay. I need to rub this because I need some space. Okay, good. Now I will be going for the loop BCDB. In the loop BCDB, okay, in the loop BCDB, if I go from B to C, I get a negative potential drop. I get one negative potential drop. Okay, because current is flowing this way, so this point will be high potential, this point will be low potential. So finally is low means change is low. Okay, minus I1 Iz, it is the amount of current into Q. Okay, then as I reach here, I see this potential difference, but this will be plus because current will be going this way, but you are coming this way, na? You will see final point is positive. I2 plus Iz into S. Now you go this way again, you are going to get plus Iz is equal to 0. Okay, if galvanometer shows no deflection, it means Iz is 0. Iz is 0. Okay, then you can rewrite the equation minus I1Q plus I2S equal to 0. I have put the value of Iz 0, so this term vanish, this term also will be vanished, huh? So you can put I1Q equal to I2S, I1 upon I2 equal to S upon Q. Okay, crisscross. This is equation number 2. Okay, you just copy it from 1 and 2, from 1 and 2, 1 and 2. You see here also left side I1 upon I2, here also left side I1 upon I2. It means you can get S upon Q equal to R upon P. Bring P here, S down. So P upon Q, R upon S. Okay, I have derived the balance condition. Okay, it is also important, huh? Their derivation is also important. You can write down, this is the balance condition of Wheatstone bridge. Okay, then you summarize it. This is the balance condition of Wheatstone bridge. This is the balanced condition Okay guys, I hope you are getting all these things. Say one question I am asking you. This is 3, this is 6 ohm, to 4 ohm, okay, and this is 3 ohm. What is the resistance between A and B? RAB, matlab resistance between A and B equal, you need to find out, okay. You see, in this problem I need to find out the resistance between A and B. You see, current will be going, it will be split into two parts, okay, again it will be split here also two parts out of this current. But you see, a condition satisfies here. This is 3, 6, this is 2, 4. 3 is to 6, it is nothing but 1 is to 2. This is also 1 is to 2. It means P upon Q equal to R upon S already there. Means this point and this point will be at the same potential. No current will be flowing. No current will be flowing through 3 ohm, means 3 ohm will not offer any opposition. As current is not there, so what is the use of this? Are you getting my point? So once you remove this, as no current flows through this, once you remove it, it is clear that 3 and 6 ohm are in series. But initially you cannot say. Initially it could not be said. No? Even you cannot find it, none of them are in series, none of them are in parallel, so you can calculate also. So once you remove, and why you remove? Because they are coming into the balance condition of Wheatstone bridge. Once you remove, you find this is 9, this is what? 6, because there will be series, no? 9 and 6 will be parallel. So what is the resultant resistance? 9 ohm and 6 ohm are parallel. So 9 into 6, 9 plus 6, okay? This is the equivalent resistance of the network, okay. So I have applied the condition, balance condition, okay. But remember, if it was not 6, something else, okay, and suppose they are not coming in the ratio P by Q equal to R by S, then you can solve at all this way, okay. We have to go to another way now, applying general way of application of the Kirchhoff's law. But this is a technique only, nothing else, okay. One more shortcut problem you can see here. Say so what is the resistance between A and B if everyone is R, okay. All the resistors given here is R. What is the resistance, okay. I think you should better give a pause and try, huh? That will, then only it will be fruitful. But I am doing it, no problem. Immediately I am doing it. See, I need to know the resistance between A and B, na? So let us unfold the picture, unfold this figure. If I put my finger at A and bring it to this point, unfolding it, so the figure will be looking like this. It will be looking like, it will be looking like this, okay. This is A, this is R, 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 and I have unfolded B also. This is B. See, both the figures are same, okay. Now you see, from this point to this point, I can apply this. I can see this is a Wheatstone bridge network only. R upon R is equal to R upon R, okay. 1:1, 1:1. It means this resistance is of no use. No current will be flowing through it. In fact, in this figure only directly you can be asked that what is the current through this R room if 90 volt battery is used there. Answer will be directly 0 because it will be in the balance condition. No? Okay, this resistor same. No current will be flowing. So to RR 2R, RR 2R, 2R 2R. When they are parallel, the answer is R. Okay, RR 2R, RR 2R, 2R 2R, R. Again, this R will be in series. What is the resistance between A and B? R and total R equal to 2R. This is the answer. Okay, that way you can keep practicing problems on Wheatstone bridge. Okay, thank you.